Hey everyone, and welcome to This Explainer. Today, we're going to completely demystify the architectural flow behind the models generating today's artificial reality. Whether it's crafting photorealistic images, synthesizing human voices, or even designing novel proteins, the seemingly magic outputs of modern AI, they all stem from incredibly clever structural blueprints. So we're unpacking the flow paths of the big three: VAEs, GANs, and diffusion models, to see exactly how they pull reality literally out of thin air. Okay, looking at our agenda, we'll start with the three paths to generative AI, dive into VAEs, GANs, and diffusion, then compare them side by side, and wrap up with when to choose which. Let's get into it. Section 1. Three paths to generative AI. Divergent pipelines, single destination. Because before we get into the weeds, it's just fascinating how completely different computational pipelines arrive at the exact same place. Now, look at how these three unique paths are separated at a fundamental structural level in this flow diagram. On the left, we've got probabilistic mapping, which relies on a bottleneck flow to compress and decompress data. In the middle, adversarial competition. Here, data flows through this relentless, competitive loop between two rival networks. And on the right, iterative stochastic denoising, a linear sequence that slowly, step by step, transforms pure static into structured information. Each visual flow here represents a vastly different philosophy on how a machine should learn to create. So the crucial takeaway here is that, whether we use VAEs, GANs, or diffusion, we're ultimately just trying to teach a machine to synthesize realistic data. That's the whole shebang. They're really just distinct mechanical pathways built to solve the exact same underlying puzzle. Moving on to Section 2, VAEs, probabilistic mapping, compressing and reconstructing data. Let's see how this approach builds a structured understanding of inputs. To really grasp VAEs, you gotta understand the concept of a latent space. See, VAEs don't just memorize exact copies of the training data. Instead, they use an encoder to map input data into this probabilistic latent space. By representing data as a mean and a standard deviation, they create this continuous, mathematically sound landscape. And this is incredibly powerful. Why? Because it allows for controlled interpolation, meaning you can mathematically walk through this space to smoothly transition from one generated output to another. It's like navigating a map of features. Tracing the pipeline of a VAE here, we see a highly structured, almost symmetrical flow. Data moves linearly right through an encoder network where it gets compressed. It then hits that bottleneck we just talked about, the latent space mapping, represented by the mu, or mean, and sigma, the standard deviation. From there, the system probabilistically samples a point in that space and pushes it out through a decoder network. The decoder's whole job is to take that compressed mathematical coordinate and reconstruct the original image as accurately as humanly possible. Now, to keep this entire flow system honest, VAEs have to balance two crucial feedback loops during training. On the left side, we have reconstruction loss. This basically penalizes the model if the reconstructed output doesn't look like the original input. But on the right, we have KL divergence. Think of this as the mathematical regulator. It forces the latent space to stay organized and continuous, preventing the model from just, memorizing data points, and forcing it to actually learn the underlying distribution. All right, Section 3, GANs, adversarial competition, the ultimate game of deception. If VAEs are a careful compression algorithm, GANs are basically a forgery ring. Instead of a single pipeline, GANs rely on this intense, head-to-head rivalry, framed mathematically as a min-max optimization game. You essentially have two completely separate neural networks, locked in a continuous loop, just fighting against each other to improve simultaneously. Let's trace this structural loop in action. The generator kicks things off by taking a random noise vector and trying to synthesize a fake image. That fake image is then fed into the discriminator, right alongside actual, real data from the dataset. The discriminator acts as our detective here, analyzing the inputs and outputting a probability of whether the image is real or fake. Based on that ruling, an adversarial loss signal flows backward, directly updating the generator's parameters to make it a way better forger next time around. It's a continuous, high-stakes feedback loop. So, how do we know when this adversarial game is actually won? Well, the ultimate sign of a perfectly trained GAN is when the discriminator's real/fake probability hits exactly 0.5. At this equilibrium, the discriminator is essentially just flipping a coin. It means the generator has become so exceptionally good at its job that the detective network can literally no longer tell the difference between reality and the synthetic data. Mind-blowing, right? Section 4, Diffusion. Iterative denoising. Destroying data to learn how to build it. Let's explore our third and currently most dominant path, diffusion models. Rather than generating an image in one single shot like a GAN or a VAE, diffusion models use something called iterative stochastic denoising. This is a multi-step sequential process where a model learns to slowly sculpt reality out of pure static. It's a completely different paradigm from the other two. Looking at the data flow diagram for diffusion, we actually start by doing the exact opposite of generation. In the forward process, we literally destroy a clean image by incrementally adding Gaussian noise over hundreds of steps until it's 100% pure static. Why on earth would we do that? Well, just so we can teach a specific neural network architecture called a UNet how to perform the reverse process. We feed that pure static into the UNet, and step by step, it predicts the noise and subtracts it, iteratively cleaning up the static until a brand new, highly detailed image emerges. Section 5. Comparing the models, trade-offs in generative mechanisms. We've mapped the three distinct paths, so let's put them head-to-head. Comparing these generative mechanisms in this table reveals exactly how they impact the learning process. Because of that intense adversarial competition we talked about, GANs suffer from famously low training stability and high mode collapse vulnerability, meaning they might just learn to output the exact same image over and over again just to trick the discriminator. VAEs and diffusion models, on the other hand, boast really high training stability and low mode collapse vulnerability, mainly because their loss functions are just much more predictable and structured. However, when we look at inference speed, how fast the model actually generates an output for a user, the tables completely turn. VAEs and GANs are incredibly fast because they operate in a single pass. Data flows linearly from input to output in one go. Boom, done. Diffusion models, conversely, are computationally heavy. Because they have to run that UNet iteratively over many steps to slowly remove noise, their multipass nature makes them significantly slower at generation time. But that slow, multi-pass approach pays off massively for diffusion models when it comes to the final result. Looking at sample quality, diffusion models earn a flawless 5-star rating for delivering absolute state-of-the-art sharpness and detail. GANs are close behind with fantastic quality for sure, but VAEs generally produce slightly blurrier outputs due to the nature of their probabilistic compression bottleneck. Finally, Section 6. When to choose which. Matching the architecture to your priority. With all these distinct flow paths and trade-offs laid out, how do you actually know which model to use for your project? Well, choose VAEs when your priority is control and structure. If you need a mathematically sound, continuous latent space that allows for smooth, controlled interpolations, like, say, morphing one specific face into another seamlessly, VAEs are absolutely your best bet. They also offer really fast inference and excellent density estimation. On the other hand, choose GANs when speed is everything. If you absolutely need real-time, single-pass generation speed, maybe you're building a live video filter or a real-time gaming application, GANs deliver high visual fidelity without getting bogged down by the massive computational loops required by other models. And finally, choose diffusion models when absolute state-of-the-art quality, maximum structural diversity, and training stability are your absolute highest priorities. If you are building a text-to-image generator and you have the luxury of negotiating on downstream inference compute and latency, meaning, you don't mind waiting a few seconds for the image to resolve, diffusion is the undisputed king of quality right now. So we've unpacked the flow of reality generation today, from the probabilistic bottlenecks of VAEs to the cat-and-mouse games of GANs, all the way to the iterative denoising of diffusion. But tracing these distinct visual flow architectures leaves us with one massive question as we look to the horizon. As algorithms become more computationally efficient, will diffusion maintain its crown? Or will a brand new architecture emerge that successfully merges the single-pass speed of GANs with the flawless quality of iterative denoising? It's fascinating space, and understanding these fundamental visual flows is the key to seeing where it goes next. Thanks for joining me on this explainer, and keep questioning the architecture behind the algorithms.